Class Connect with Arikewuyo Yusuf. In our last class, we looked at dimensional analysis, and we were able to establish that dimensional analysis can be used in getting equivalence between a formula and a quantity. And we established the fact that quantities can either be derived or basic, otherwise called fundamental. Recall that fundamental quantities do not depend on other quantities for their existence, and derived quantities depend on the fundamental quantities or other derived quantities for their existence. In today's class, we shall be looking at further examples on dimensional analysis. For example, if we are told to obtain the dimension for pressure, what we need to do is to ask ourselves, what is the formula for pressure? By definition, we define pressure as the force per unit area. This implies that pressure will be equal to force over area. And of course, force is a derived quantity, area is also a derived quantity. We recall from our last video that force is the product of mass and acceleration. Let me take this off. So this implies that if we represent pressure with letter P, force with letter F, and area with letter A, we would have P equals F over A. But we know that force has a dimension of mLT raised to power minus 2 from our previous lecture. Area, being derived quantity, is the product of length and length. Therefore, area will be given as L times L. Let's take the next slide. So that we have area equals L squared. And therefore, our pressure will be given as mL T raised to power minus 2 divided by L squared. By indices, we are going to have m L T raised to power minus 1 T raised to power minus 2, which gives the dimension for pressure. You can be asked to show if pressure, stress, and Young modulus are dimensionally equivalent. To do this, all we need to remember is the fact that both pressure and stress, as well as Young modulus, are all defined in the same way. The area of use is what differentiates them. Pressure is given as force per unit area. Stress, otherwise called tensile stress, is also the ratio of force per unit area. Then Young modulus is given as the ratio of tensile stress over tensile strain. So that for Young modulus we shall have, let's depict it as Ym equals stress over strain. Okay, so that stress we know is given as F over A, and strain is given as extension over length. Let's go to the next slide. Since we have our Young modulus given as FA over A divided by E over L from previous slide, this implies that our Young modulus in terms of dimension would have mLT raised to power minus 2 for force divided by L squared for area, then divided by extension is also length divided by length. Looking a little bit confusing, but we can arrange it as follows. M LT raised to power minus 2 divided by L square, then divided by L over L. Let's take the next slide. So that we shall have M L raised to power, MLT raised to power minus 2 divided by L raised to power 2, and of course L divided by L gives 1, so that we have M L T raised to power minus 2 divided by L raised to power 2, and by indices we shall have M L T raised to power minus 1 T raised to power minus 2, which of course gives the same as what we obtained for pressure. Therefore, Young modulus, stress, and pressure are dimensionally equivalent. Let's consider this question. At what respective values of x, y, and z will the unit of impulse be dimensionally equivalent to m raised to power x, l raised to power y, and t raised to power z? This particular question is actually asking us to get the dimension of impulse and tell what the values of x, y, and z will be. This we shall do as follows. Let's represent our impulse with letter I. And of course, by definition, we know impulse is the product of force and time. It is also equivalent to momentum, and as such, we can say impulse equals mass times velocity, since momentum is mass times velocity. Alright, so let's go on with this. We're going to have, since we know the dimension of force as m, l, t raised to power minus 2, and we know the dimension for time as capital letter T. It is a basic quantity. This implies that by simplification, we are going to have m, l, t raised to power minus 2 times, okay, let me take this off, okay, we're going to have minus 2 plus 1, since the t's are the same. Then we'll have m, l, t raised to power minus 1, which gives the dimension for impulse. Now let's check if using the product of mass and velocity, we shall get the same values. To check if the product of mass and velocity gives the same result as obtained earlier in our previous slide, we shall have impulse equals mass times velocity. And of course, we are going to have impulse equals, since mass is a basic quantity, it has a dimension of capital letter M, and velocity has a dimension of LT raised to power minus 1. Therefore, impulse equals m, l, t raised to power minus 1. Since the question asked us to get the values for x, y, and z, we can say, therefore, x, y, z equals, if we look at the powers of m, we have that m is raised to power 1, l is raised to power 1, and t is raised to power minus 1. Therefore, x has a value of 1, y has a value of 1, and z a value of minus 1. Thanks for watching. Hope to see you in our next episode. Don't forget to subscribe. Thank you.